So here's the airfare data that we were looking at. And while I kind of drew an estimate of the line and where it was landing, what I drew here on this picture is the exact line. So what we can do is use technology in order to find, or not even use technology, but we'll have a formula for finding the equation of this line, and it's called the line of best fit. There are a few other names for it. It can also be called the least squares regression line, or sometimes it's even just called the regression line. Essentially, in this section, if you're asked for the equation of a line, that's what you're going to want to find here. So to draw this, what we can do is, if we've drawn our scatter plot, we just use a ruler straight edge to draw a line through the data. And what we want to do is think about our individual data pieces as we do this. And when we draw this line, we want to try to fit all of the data simultaneously, as close as we possibly can. Now, like in this data, that's our data value for Miami up there. It's pretty far away, which is affecting our line. It does pull the line slightly towards there, but it's really focusing on kind of the average of the data and how to fit as much as possible at once. So when we get this line, maybe we're going through points, but most often with enough scatter, we're kind of away from the line. What we can do is use this line for predictions, so that if we see this data, we have this association, then what we can do is start estimating, so that if I started to look at traveling, maybe I'm looking at traveling 1,100 miles. So I choose some distance. If I wanted to estimate the airfare, what I could use is what is the output from that line. So maybe I'd spend about $250. So we can use this line to start making predictions based on, if we choose some value for X, what would be our possible Y value. Something we want to evaluate here are residuals. Now residuals, visually, what that would look like is, say we're out here at this dot. Our residual is this distance between our observed value and our predicted value. So something to notice, these dots here, that's from our original data. This is what we would call an observed value. And there's some X and Y coordinate to it. So it's like there's X, and then it's a Y value from our data. Predicted values are going to come from the line. So if I have this point right here on my line, that is a predicted value. And with that, it'll be coming from some X value. But then for Y, it is a Y coordinate, but it's a Y coordinate from our line, which we use Y hat. So if we jump down to the equation for our line down here, let's see. For our equation of the line, we use Y hat to represent our line of best fit. And then the setup here is very similar, if not pretty much exactly the same, as our y equals mx plus b from algebra. So m was our slope in algebra, and b was our y-intercept. Same thing here. B1, though, and just in terms of using this with two numerical variables and talking about linear regression with scatter plots, instead of using m, we use B1, and then for y-intercept, we use B0. So that y hat is coming from our line. So with that, there's kind of two types of coordinates that can show up. It's either observed and from our data, so observed values coming from our data, and then predicted values are coming from the line. So the residual is going to be the difference between this data value and the predicted value. So residual, you'll take your observed value, so that's coming from the data. So you'll take your y coordinate from the data, minus the predicted value, which is coming from the line, which maybe we'll need to calculate what that value is, but it shows us a difference between those. Now, when we find this distance, so let's say we were doing this for let's see. Let's say we were doing this for Miami. It's going to have a very large residual. So our y value's up here, our y hat is down there, and we would use the subtraction between the two. Now if we did that, if we thought about our possible outputs there, we'd have this large y value minus this smaller y value. So what will happen is up above here, if our data value lands above the line, when you calculate your residual, it's going to be positive because you'll have this large y output from the data subtracting this smaller y output from the line. Then when we land exactly on the line, so let's say we were looking at this kind of third point here. Let's say it is exactly on the line. If I tried to draw the residual there, I don't have anything to draw because there's no distance between the data value and the line. So if I calculated the residual there, if we land on the line, the residual is just 0. If we land below the line, so let's say we're at this point here and we're looking at this distance. So again, on the line is my y hat value, my data value is y. So residual always goes observed minus predicted. So in this scenario, my observed value coming from my data is kind of low. It looks like it would be below $100 here. And then from the line, we're getting something much larger, maybe like $170. So with this, I'd be taking a small value and subtracting a large value. So with these values below the line, your residual is going to be negative. And this tells you something about how the line is operating as a prediction. So like, let's say we looked at that Miami scenario up above here. So let's go back to that first case where we had positive outcome. That would be the scenario of I'm buying a ticket to Miami. What they predicted for me was something low, like about $200. So they predicted about $200. I went to pay for my ticket, and actually I had to pay over $300. That case there, how that line operated in prediction, they underestimated what was happening. That was an underestimation. They told me something much lower than what actually occurred, which isn't a great scenario for this case. So with that, if you get a positive residual, that'll link to the line underestimating. When the residual is 0, so if we go back to this case here where we're landing exactly on the line, so we were traveling, about 380 miles maybe, and then the price was about like $130. So with this case, in terms of prediction, I said, I'm going to travel these about like 380 miles, and the line predicted, okay, you're going to pay about $130. And then I hop on whatever website I'm using, go to buy the ticket, and it is exactly as predicted. So when the residual is 0, this estimation is exact. They got it exactly right for us. Then when the residual is negative, so this case that we looked at in the middle here at, let's say that is, we'll just estimate 600 miles. It's that I was going to travel 600 miles. The predicted cost was maybe like $170. So I was going to buy my ticket. They said, we expect it's going to be $170. And when I go to buy my ticket, it was actually about $100. So it was much lower than expected. So with this, the prediction was an overestimation. So when you find this residual, what you can do is, when making a sentence, describe it as an underestimate, overestimate, or maybe it was exact. The exact scenario doesn't happen too often, but if you get that residual of exactly 0, that's how you'd interpret it. All right, our equation for the line and how we're going to be using it. So like we were saying, that y hat is giving you a predicted y value. So it's like choosing some value for x, and that's what we predict to happen. But then what we can see from the scatter plot itself is the actual observed data. B1 is the slope. So it tells you how things will increase and decrease. And a sentence form that we're going to use, and we'll look at interpretation here, we say like, if we increase x by 1 unit, that slope, or actually let's say y will increase or decrease, depends on if the slope's positive or negative. If the slope's positive, then we'll increase. If the slope's negative, then we decrease. Y increases or decreases by whatever the slope is units. So we'll look at making sentences for slope. Now for calculation, this right here is our formula for slope. So what we're going to do is take the standard deviation of the y values divided by the standard deviation of the x values and multiply that with r. So S there, as a reminder, is standard deviation. Remember, with our data, we have these two columns. We have x and y data. So in that numerator, all they're doing is focusing on just the y data and taking the standard deviation of that. And then for the denominator, they're just looking at the x data and taking the standard deviation of that. So what we can end up doing is, if we have our original data, we can collect this information. We could collect standard deviation for each. And then what will help with intercept is our formula here, which uses the means. So this y bar, that's the mean of the y values. And then x bar is the mean of the x values. So same notation that we've been using all term, it's just now we can also apply it to y as well. So if we had our original data, we could also find x bar and y bar. Those two values will be given to you. What I'm going to do, and we can kind of look at the example we're going to do next, I will give you this table that kind of tells you your x value, your y value, and then you'll get mean, standard deviation, and your value for r. With those pieces, you can use this formula to find slope and intercept. Now, in the interpretation for the y-intercept, this is the case where it's what happens if x is 0. So if x is 0, then y is whatever the intercept is. Sometimes this sentence makes sense, sometimes it doesn't. Slope, we can always write an interpretation for. Intercept, we can try to write it, but sometimes it doesn't make sense in context, so it'll just kind of depend. All right, so let's apply all of this. So you're given the descriptive statistics here. You have mean, standard deviation, and your value for r. So we want to find the least squares regression line, meaning we want to find this y hat equals b1 plus, b1x with the intercept there. Order doesn't really matter, but what we end up wanting to do is find slope and find the intercept. Let's go ahead and start with first step, find slope. Actually, order does matter because we need slope in order to calculate the intercept. So we have to do slope first. So using the formula for slope, we'll take the standard deviation of the y values, which is that 79.4932. And what we're going to do is divide by the standard deviation of the x values, which is the 402.6858. And then multiply that with r, which is the 0.6953. And when we do that, that should give us a slope of 0.1373. So that gives us the slope. Then what we can do is find the y-intercept. So finding the y-intercept using our formula, we take the mean of the y values, so that 179.5833. Then what we're going to do is subtract the slope, 0.1373, times the mean of the x values, which is a 712.6667. So what we'll do is plug that into the calculator. and that should give us a y-intercept of 81.7342. So for our formula, our least squares regression line is equal to slope times x plus 81.7342. So that's how we'll find our least squares regression line. Calculate slope first using the formula, then calculate the y-intercept, and then put it all together for your final answer. Now our slope. So we found this slope of 0.1373. So writing our interpretation and fitting what I wrote up above, what we would do is talk about if we increase x by 1. So again, x in this case is distance, and y is airfare. So what we want to look at is if we increase x, which is distance, by 1 unit. So distance units in this case is miles. So if we increase distance by 1 mile, then we can talk about how y is changing. Airfare is going to increase or decrease. It depends on whether the slope is positive or negative. We have a positive slope, so airfare is going to increase by, and then what our slope is in units, which in this case, it's money. Like airfare is in terms of dollars. So you could do is like by 14 cents. So what this tells us is there's this change in terms of units of our slope. It's like dollar per mile is what's occurring. It always goes your y units over your x units. So it's that we're getting these 14 cents per mile increase for these airfares. Then for interpreting the y-intercept, so y-intercept is that 81.7342. So what this would translate to is, what if x is 0? So if distance is 0, airfare is $81.73. Now, in that form of interpretation, it doesn't make that much sense, because if we're not traveling anywhere, we wouldn't have an airfare. But what you could think of this as, how it could be interpreted, is this kind of base charge. No matter what, you're going to have this $81.73 charge, and then from there it increases based on distance. So it could be seen as that way. But again, sometimes these won't make sense at all. Like sometimes this comes out to be a negative number that just doesn't interpret well in sentence. But this could be seen as base charge of $81.73. All right, and then our last question here is to make an estimation. So what we can do is estimate the cost of a ticket if they're traveling 200 miles from Baltimore. So what we can look at here is we want to estimate airfare. So what we're going to do is plug into our formula. So we have our 0.1373, and then plug in our x value of 200 miles plus 81.7342. And when we plug in that value for x, we'll just solve with our calculator, and that will give us an airfare of 109.1942. So if we travel 200 miles from Baltimore, we expect an airfare of $109.19. So some key wording in there is to throw that this is what we expect to occur. It's an estimation, because maybe they observe something completely different. Maybe we have a part E here that says we bought a ticket for 200 miles with an airfare of, let's say it was $150. So now what we have are these two scenarios. It's like that $109.19, that's a prediction. And then what they're stating in this sentence for part E is an observation. So this is where we can get to, so I realized there wasn't an example with residual, but we could evaluate residual here. So we take our observed value, which is that $150, subtract our predicted value, which is the $100.19, and we can look at the difference between what we expected to happen and what actually happened. So this will give us a positive 40.81. So we can see happened here is the linear model that we used in terms of for our prediction. It underestimated, right? Because we ended up paying more than what we expected. It underestimated by $40.81. So sometimes we'll have these comparisons of what we expect to happen and what actually happened, and that's when we go to residual to find observed minus predicted, and then evaluating whether our line overestimated or underestimated.